So we're going to be talking about acid and bases. Okay, so now if we think about an acid, right? So how did we define an acid before? Do you remember?
No.
You don't remember?
I have to review.
HCl, AQ, right?
Oh, yeah.
Yeah, so think about this, right? An acid is going to be defined as what we call a proton donor, right? So in other words, what we're going to do is this guy's going to break down into two parts.
Yes.
Draw it like this, right?
Oh, okay.
Right? It's going to ionize, right? So, but if we think about this guy is just a proton. It's an H plus, which basically means all you're giving them is a proton, okay? So that's often why we call it a proton donor, right? And a base is going to be a proton acceptor because it wants to accept it to kind of get like water, right? So okay. Can you see that? It's clear.
Yes.
Acid, base, right? So often when we think about bases, we think about that OH, right? And then as an acid, we always think about that H plus, okay?
I'm sorry, can you repeat that?
I said when we think about acids, we think about H plus, and then when we think about bases, we think about OH, hydroxide ion. Okay? So if we think about water, water goes through this process called ionization. Okay, so this here represents equilibrium. That basically means that you have the existence of both the products and the reactants at the same time. The amount may vary, right? For instance, there's very little of this, it's mostly this, right? So when we have a glass of water, we basically have this and we have these ions in it as well too, okay?
I can't see when you say this and that.
Oh, that's right. Let me figure out how can I say it? This, will that help? Can you see now?
Yeah.
Okay, so we have a combination of this and we have a combination of this. Gotta figure out a way.
Okay.
Okay. So when we talk about having the existence of both, that's what these arrows here mean, right? So that's basically representing what we call equilibrium.
The two arrows.
Yep. Now, what equilibrium means is that the rate of this forming, meaning our product side forming, and the rate of our reactants going back to our reactant, right, is at the same speed.
Is at the same speed?
At the same speed, yes. Right? So in other words, once you get to equilibrium, you're basically keeping it flowing consistently. Let me also get my, so you can see me as well. Hold on. Or are you able to see me in the classroom?
I hear you very far.
You hear me very far?
Yeah, so it's hard to understand a little.
Okay, so I'll work on that part. Let's see. Is this better now?
When you talk,
Yeah. Can you hear me better or not?
you still sound kind of far.
Okay. Let's see. Student, but you know, it doesn't change.
Now I see a person in class.
Yes, you see my,
Oh,
yeah. So I'm setting it up so you can see me. Okay, is that better? Can you see me completely? So, and then you'll also see the white screen. I don't know if you're going to be able to hear me or not. Let me know if there's still audio issues. We're going to try to do the best we can. Okay, so this here basically means equilibrium. Like I said, that means that in this direction, it goes from from reactant to product to make our products, and then it goes back at the same speed. Okay, so that's essentially what equilibrium means. And it kind of like, it's like when it's normalized, when, like, have you ever cooked something and you just let it keep cooking and it boils and boils and boils and then it just kind of levels off? Right, and you can see it continuously boiling at the same speed and things like that.
mhm.
Okay, so it's kind of like that, right? Where you just get that point where you just find that equilibrium point, okay? And so that's what equilibrium essentially means. Now, what it means mathematically is there's this constant called, in this case, it would be called Kw, or the equilibrium constant for water. Okay, and now when you're talking about the equilibrium constant, the only thing that's going to be able to affect the equilibrium constant is going to be things that are aqueous and gases. Okay, so liquids and solids aren't going to affect, because like say, for instance, if we had a liquid and we had water, we put the water in and we put this other liquid, and we know that they react, right? Their reaction is only going to be at the surface, okay, where they're both meeting, okay? And if it's a solid, that's also going to be the same thing. It's going to react to say we had a rock or something, and the reaction is only going to be at the surface. It's not going to be through and through. But if we have something that's aqueous, it's going to be able to flow into each other and react normally, right? So you're going to get a nice little rate that's going to happen. Okay, so equilibrium is only going to be affected by aqueous solutions and gases. So when we write our equilibrium constant, AW,
Hold on, give me 1 sec. You said it will only be
affected by,
aqueous and gases.
that's right, aqueous and gases.
Baby, mommy's in class. Close the door.
The way that we would write the equilibrium constant, we say the equilibrium constant, Kw, is going to be equal to the concentration of both of our aqueous solutions. So it's going to be of the concentration of H plus. So the brackets means concentration. Sorry, I ran out of room. Concentration. Okay. And O minus, okay? I'm sorry, OH minus, okay? So that's what it's going to be for water. Okay. Now, the equilibrium constant is a constant, which means that it's always going to be the same value. The equilibrium constant is always going to equal 10 to the minus 14. Okay. Now, we know about chemistry, right? And we know that these represent quantities. So I have one of these, and I have one of these, right? I have one of these and one of these. Is that correct?
Yes.
Okay. So now since I have one of these and one of these, and I'm breaking down one water, that means that every time that I break down one water, I'm going to have one of these and one of these. So these guys are going to be equal in their concentration, right? Because we define our concentration based upon molarity.
Mhm.
So moles are going to be equal. And since it's all in the same solution, they're going to have the same molarity. Okay?
Mhm.
So if that's the case, then we can sit there and say that concentration of HOH are equal to each other. So then I can substitute that in there, and I can say that H plus squared is equal to 10 to the minus 14. Or I could say H plus, concentration of H plus is equal to 10 to the minus 7. And that would be both. Okay. All right, with me so far?
Yeah, it's just a little hard to, because when I see you on my screen,
Yeah.
everything is backwards.
Oh, it's backwards, huh?
Yeah.
Let me write that down.
But I see it, so it's either I see what you're writing or I see you like standing and giving the lecture.
Okay, that's a very good point, because then we'll have to, can you do me a favor, take notes? So they see backwards if they look at.
And we see it very small because
Yeah, how does it show up on the screen though? I mean, here, how does it show up on the?
I could see it.
But it's still kind of small.
No, it's good, but when you're writing, it kind of covers,
Okay,
or when you point, it kind of covers.
okay,
I don't know, it's a little hard.
okay. That's good. We're testing out new technology here, so. We need to get all the kinks out. Okay, so now you've heard of pH before, right?
Mhm.
Okay, so pH is this scale that we use to determine if something is acidic, basic, right? So pH goes from 0 to 14. Okay, so if the pH is 0 and less than 7, say 6.9, it's considered to be acidic. If the pH is 7, it's considered to be neutral. And if the pH is greater than 7, so 14, is considered to be basic. Okay. Now, pH is the scale that we use to determine whether an acid is a strong acid, or if it's a weak acid, or if it's a base, right? So, the way that we calculate pH, pH is going to be equal to minus the log, this is log base 10 of the concentration of H plus. Hence, we get pH. Okay. So if we plug this in for water, pH equals minus log 10 to the minus 7, log base 10 of an exponent to the 10th power is going to equal that number. So that's just going to equal minus 7, which is just going to equal 7.
Oh, so that's log, not
Yes.
10.
Yeah, that's log. Log, and that's base 10. Okay? Exponent to the 10th base. So this is log base 10. So that means it's based upon factors of 10. Okay? So now this tells us that the pH is 7. So that means water is neutral. Okay? So that means that the number of H plus ions are going to be equal to the number of OH ions. So if we calculate pKW, and that's just based upon this definition, KW was, so in other words, we get the log minus the log, KW is going to be equal to minus the log of H plus times OH minus. And this is just math, you know. So if we break it down, this here is going to be defined as pKW. And that's going to equal, if we know the rules of logs, we get minus parentheses log, and when it's multiplied by each other, it's the same thing as saying log of H plus the log of OH minus. Or we can break this down. We know that minus log of that concentration is just equal to pH. So pKW. Do you mind if I erase our water equation?
Yeah, that's fine.
So again, pKW is equal to pH plus pOH. We know that pKW is always a constant, it's always the same thing. That's always going to equal 14. So we get 14 is going to equal pH plus pOH. Okay, so now this helps us determine if we have the concentration of the hydroxide, then we know we're able to sit there and calculate the pH by using this equation right here. Okay? Does that make sense?
Mhm.
So let me give you an example. Okay? If we have a solution, it's a 10 to the minus 3 molar solution of sodium hydroxide, what is the pH? So in this case, we're saying that we have sodium hydroxide, which we know ionizes the sodium and the hydroxide ion, right?
Mhm.
We know that it's going to be in equal parts because it's 1 to 1, right? So then to calculate, we want to calculate the amount or the concentration of OH. So we know that we have our concentration of OH is equal to 10 to the minus 3 mole. So if I wanted to calculate the pOH, that's going to equal minus log the concentration of OH, which in this case is going to be minus log 10 to the minus 3 molar. So then that's just going to be 3.
What is the minus log?
It's on your equation, minus log, it's minus, the sign minus. Log is the math function that we use, log base 10. So on your calculator, you have a function that says log. So let me pull out mine. So the log is right here. Log base 10.
Mhm.
It's a little delayed. Hold on. Still
You need to put it up a little.
put it up a little.
Oh, that's perfect.
So you guys are able to see it.
Mhm.
So in this case,
Now it's blurry. Oh, there it is.
okay, so we're going to use that function, right? So it's minus log, so we go minus, oops. So it was 10 to the minus 3, right? So we're put that as minus 3, 10 to the exponent, right? So that's what 10 to the minus 3 is. And then we take the log of that, log base 10, we get 3, and then we change the sign, okay? By using minus, plus and minus up top.
How would you do that on a calculator?
That's what we just did it on the calculator.
Like, not on the phone though.
It's the same key. It should be log on your calculator. It'll say log.
Mm-hmm.
And so you enter the,
Got it.
yeah, it's exactly the same thing. You have a plus and minus.
Mm-hmm.
Okay.
So first we put in the 10 minus 3.
Yes, first you would put in the 10 minus 3. Yeah. So yeah, you put in a 10 minus 3 first. And does that make sense?
Yes.
Does that show up backwards on your screen? It shows up backwards on my screen. But it
Yeah.
shows the right way on your screen, doesn't it?
Yeah, it looks right.
That's right. Okay. That's so weird. So does that help how to use log?
Mhm.
Okay, so we have the pH, the POH. OH is equal to 3, right? So if the POH is equal to 3, then what must be the pH? How would I figure that out?
Can you repeat the question?
If the POH we calculated was OH, if that's equal to 3, right? What is the pH? Because that's what we're looking for. We're looking for pH. How would I calculate that?
Would you do the 14?
That's correct. So then I would change this equation. OH. So then 14 minus 3 equals 11. Right? So that's how we calculate my pH.
Wait, where did you write it? Up on the top?
Right.
Okay.
Okay. Okay, so let's try another one real quick. So, hi Robin, how you doing?
Doing all right, thank you. You?
Good, good. How's the project coming?
It's coming.
Oh, so you're done already? Is that what you're saying?
Now,
Oh, okay. So if I have okay, if I have concentration of potassium hydroxide of 10 to the minus 9 molar, what is the POH and the pH of the solution?
So you would start with the OH negative equals 10 to the negative 9 molarity.
Okay. So POH equals negative log 10 to the minus 9. Plug that in, you should end up with 9. Okay. And then
So that's the POH, and now we want pH.
Yep.
So we will do the pH equals 14 minus the POH, which is 14 minus 9, 5.
okay. You see it?
Did I do something wrong? I got 8 for the POH.
You got 8 for the POH.
Yes.
So yes, you must have done something wrong. So the way you want to enter it is, it would be 10 to the whatever power
Right.
minus 9, right? And then we take the log of that. And then that's going to give you minus 9, because log base 10 of the numbers of that exponent is just that number. So it's going to be minus 9, but it's also a negative in front of it, right? So then it's negative. So you're just switching the sign.
I kind of see how Robin got 8, because on the calculator, if we do 10 and then for the exponent, we put EE.
No, so what you would do is, that's the reason why, because
Okay.
what you're saying is EE represents 10 to the, that's what EE equals. EE equals 10 to the X power, whatever number you put there.
Uh-huh.
So, but if you put 10, and then you put EE, and then you put, let's say 9 or minus 9, right?
Yeah.
That's an extra. Right? You understand?
Oh.
So that's the same thing as saying 10 times 10 to the minus 9. Okay, well, you need to write, in that case, you want to put 1 times 10 to the minus 9, or 1 EE minus 9, or 1 EXP minus 9. Is that, do you understand?
So 1 EE.
Minus 9.
So that's how we would put it in here.
Yeah.
In our calculator.
Yeah, you can put it in your calculator.
So 1 EE minus 9. So
Yes.
whatever, okay.
But if you put 10, then you're saying is 10 times 10 to the minus 9.
Okay, that makes sense. I just
Yeah.
had a confusion about notation there, and I wasn't expecting that. So
Okay. So that's, yeah, that would be the reason why that you got that.
okay. So then it would be 14 minus 9, which is 5. So it's going to be acidic, right?
Yeah, that's right. It would be acidic. So our solution is acidic. Good job. Piece of cake, not too hard.
Not terribly hard.
Okay.
Can we do another one?
Yes.
Yes, please.
So POH. The POH is 3.
Are you sure?
Well,
Okay, what are we looking at? What is our reaction here? So we have HCl.
yeah,
What does HCl break down to?
H plus Cl,
H plus
Cl negative.
and Cl negative. Okay, is that OH?
Oh,
Okay, so what do you have now?
so would we do the same thing?
Yeah, you do the same thing, only thing now you're doing it for pH rather than POH. Now you're given the pH instead of the POH, so you have to calculate what the pH is. So first. Okay, so how do I do that? pH is going to equal what?
Be 3. Would
Okay.
the POH be 11?
So it'll be minus log of 10 to the minus 3. And then that's going to equal 3. So then POH is going to be 11. That's right. POH is going to equal 14 minus pH, which is going to be 14 minus 3, which is going to be 11.
So it's acidic.
So it's acidic. Yeah, that's right. The pH, look at our scale, it's going to be acidic. Okay. One more.
Yes.
Okay.
Okay, so just to make sure I understand this correctly, so whichever, so if the H plus is present, then you're calculating pH. If it's the hydroxide that's present, then you're calculating POH, and then and then to derive the other, you just do 14 minus the value, right?
Yeah.
Okay.
So the pH would be 12.
Well, initially it was 12. I changed it to 2.
Oh,
Yeah, sorry. So 2. Yep. So it's minus log 10 to the minus 2, which is equal to 2. So then my POH is going to equal,
is 14 minus 2 is 12.
okay,
And it is acidic.
that's correct. Okay,
No, it's going to be base.
what was that?
It's going to be base.
No, is it going to be a base? You just
Oh, the pH. Never mind the pH. Yes.
remember, you always use pH to determine whether it's acidic or not. Okay? You guys good?
Yes.
Okay. Okay, so let's go deeper into equilibrium. Just a little bit. So I'm going to give you a generic equation for equilibrium and how to calculate the equilibrium constant. Okay, so let's see. Say we have So when we define the equilibrium constant in this case, it's always going to be products over reactants. And we call it KEQ for equilibrium. Okay, so in this case, the way we write it is, it's the concentration of C. Coefficients act as an exponent. So to the second power times the concentration of D. This is 1, it has a coefficient of 1. And then it's over reactants. Concentration of A. Now we don't include B because B is a solid. So solids and liquids we don't include for equilibrium. Only gases and aqueous. Okay, so let's say I have this generic equation. Okay.
So this is an example.
Yep.
And when we write the equilibrium constant, we don't have to put if it's a gas or
Yeah, or aqueous. No, we don't have to do it. Yeah.
okay. So so would it be bracket C and then
KEQ equals, is it bracket C?
yes,
Okay.
and then bracket D with an exponent 3.
Okay.
And then over bracket G and then bracket H with to the second.
Okay. That's it.
Is this going to be on our final?
Yeah. 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 Wait. Okay, you want to try one more, or you guys got it?
One more, please.
Then we'll expand on it just a little bit. Let's do a real simple equation. Sorry. You gotta put it down here. Okay.
So would they be included in the same bracket? Like magnesium fluoride?
That's the compound, right? It's the concentration of the compound.
And because it's 2, we wouldn't use that as, no, only the coefficients go as exponents.
That's right.
Okay. So would it be KEQ equals bracket MgCl2?
MgCl2, are you sure? Because what is the rule? Is it what goes on top?
It would be the product.
It should be the product.
Oh, that's right. That's okay.
So it would be magnesium nitrate.
Yeah.
Mg. Okay.
And we wouldn't use
That's right.
because it's a solid. This
That's good.
So then on the bottom, it'd be bracket MgCl2. And then bracket silver nitrate, and then with an exponent 2.
Okay, that's it.
So it's product overreacted.
Okay. Okay, so let me teach you one more thing, and then we'll do a really complex problem. Okay? Okay, so now let's assume that we have a, in this case of this upper reaction, I'm gonna did you guys get the second part done, written down? The lower half with the silver nitrate, you got that written already? Now let's assume that we have a reaction. This reaction up top, okay? So that A plus 2B yields 2C plus D, right? That reaction. Okay, now I had another reaction that basically removes D. So it takes D away. Okay, now in equilibrium, since both sides are moving in equal directions, right? Okay, now if you remove something from one side, it's going to affect that equilibrium, right? Something that's involved in that reaction. Okay, so if I remove D, it's going to cause the reaction to go in the forward direction. This is called the forward direction.
It's called the forward direction.
Forward direction. I like to think of it as it's favoring. The arrow points to the side it's favoring. Okay, so it's favoring the products. So in other words, the reaction is going to start making more of the products because we remove D until it gets back to equilibrium. Okay,
Can you repeat that one more time?
I said, if I remove D, the equation is going to push it in the forward direction until it gets back to the same amount of D that should be there. So back to that equilibrium value. Okay, so it's going to drive the reaction forward so we can make more D.
So it's going to do that until it reaches equilibrium again.
Oh, yes, until it reaches equilibrium again. Yes. Okay, that's called the Chpater's principle.
The what?
The shot. Yeah.
French guy's name.
Yeah, some French guy. The Chpater's principle. I probably butchered spelling his name.
Like,
RS.
It's A what?
So
the Chpaters.
CHAPELIER.
CHA.
T.
T.
ELIER.
The Chpater. Okay, the Chpater's principle. Okay. So, and that just basically means shifting. So it's going to be shifting to get back to equilibrium. Okay. So if another situation. If I dump in a whole bunch of A, which way is it going to shift the reaction? To the left or to the right? To the products or towards the reactants?
If you add more of A,
Yes.
is it going to shift?
It'd probably shift forward again because you're giving more like fuel, if you will.
So it's going to go forward again. Right? Now, if I added temperature to the reaction, and that's let me add. Let's say it's an endothermic reaction. Okay, it's an endothermic reaction, and I add temperature to the reaction. Which way is that going to shift the reaction?
Shift forward again?
That's right, it's going to shift forward.
Because, okay, so endothermic is you're adding heat to the system, right?
That is correct.
Okay. That is something that I will always have to think out loud.
That's all right. Okay, you guys got it?
Almost. I can't write as fast as you talk.
All right. I talk fast too.
So when you add heat, it's endothermic and it moves forward.
So then if it were an exothermic reaction by adding heat, would that shift it left?
That's correct. That was shifted towards the products, yes. And the reverse reaction. So it was exothermic. That means that we're adding heat here. So exothermic. That means that we'll be driving it in this direction. Okay. Now, if I add B,
So exothermic is when you're adding heat to the product.
exothermic, no. Endothermic is when you add heat to the product. You're putting heat into the reaction. Endo, meaning in, thermic, heat. You're adding heat to the reaction. Exothermic means that you're releasing heat. Okay, so that means it's on the product side. So if the reaction was exothermic, that means that we will be putting heat into this system. That's going to drive the reaction the other way. So it's going to try to get back to equilibrium by getting rid of some of that heat. And so it's going to go back towards the reactants. Does that make sense?
And if we added B, would it shift left to compensate for the reduction of A?
No. Because it's not dependent on B, because B is a solid.
Oh, right. Okay.
So no effect.
No effect. Okay, right.
Okay. Let's do this.
Is this an example?
Yeah.
So first, do we determine the pH?
Yep,
Like before we change?
yeah, well, the equilibrium constant isn't gonna make a difference, it's always gonna be the same regardless. It's gonna be the same equation, so it's not gonna be dependent on the pH. Okay, initially, right? So the pH of it is gonna be the same at the very beginning. And then as it gets to equilibrium, there might be some changes, so.
Mhm.
Okay. But you're not gonna calculate that, just do the first part,
Okay.
okay? And then, let's see. Okay.
So the equilibrium constant is KEQ.
Okay.
Equals the product over the reactant.
Okay.
So we wouldn't add the H2O because it's liquid.
Okay.
So it would just be NH3. Over bracket NH4OH. And so now we find the pH.
So how will we find the pH?
So we have 10 to the negative 25 M. So if we,
That's negative 2.5.
mhm. Oh, 2.5.
Okay, thank you. Because that was, yeah, I was like,
It would make things a little bit harder.
yeah. I have to break some physics. Something. So would the pH be 11.5?
Okay. We know that the POH equals minus log 10 to the negative 2.5. Then 14 minus 5 is 11. Okay. And then the last part,
So if we remove the NH3, it would go forward.
That is correct. Piece of cake?
And then is there a numerical value for the K equilibrium?
So it's usually given to you. So there's a table for all reactions, right? And that's going to be your K equilibrium. Or
Okay.
you'd have to determine it experimentally.
Oh, I see. Okay.
So there's this big book that has a lot of them listed. So.
All right.
We're going to be talking about nuclear chemistry. I'm going to show you a couple slides too, not too many though. So when we talk about chemistry, we're mainly
Sorry,
talking
chemistry?
nuclear.
Yeah.
Okay, so when we talk about nuclear chemistry, we're mainly talking about radioactivity, right? So. Okay, so that's just basically emission of rays and particles from the atomic nucleus. Yeah, if I can spell. Okay. So particles that we have what we call the alpha particle.
Oh,
Okay, so during the emission of alpha particles, or what we call alpha decay. So in that case, we're going to be, hold on 1 second. So during alpha decay, we're going to be basically emitting alpha particles. So okay, now the alpha particle is just going to be helium-4. Okay. So do you guys remember when we did isotopes and everything, and back in the old days when you first started this endeavor?
mhm.
Right.
Okay, so we know that the bottom number, this number here,
Is the number of protons.
yep, it's the number of protons, also called the,
Oh, atomic number?
that's correct. And then the top number,
Is protons plus neutrons?
that's right. Protons plus neutrons. Okay. And it's also called the,
Oh, it's
Mass.
mass number. That's right.
oh, okay.
Okay. Okay. So now what's happening in the case of alpha decay is that we're basically releasing that helium isotope from an atom. Okay, so we're kind of removing it. Okay, so let me show you an example. Then we'll talk about beta. Everything down so I wouldn't screw it up. Okay, so okay.
Is that thorium?
Yes, that's right. It is thorium.
Okay.
Okay, so if we take a look at it, right? So we get our alpha particle or that helium isotope, and then we get whatever's left over, right? So we started out with uranium 38. So we end up with thorium 234, right? And then we have two protons that are being released from the helium, and we have 90 protons that's going to be remaining. So that's how we know it's thorium that's going to be remaining, right? Because we look at a periodic table, it'll be 90, and we know that it's a TH, right? Switch screen.
So we're releasing helium.
We're releasing helium, so that's the alpha particle, and then we get the remainder, what's left over, right? And so that's going to give us a radioactive material. So we're going to have that thorium, and then it's going to be thorium and whatever mass is left over. Okay, so we have a radioactive thorium 234, right? See that? Okay, so if you take a look, the helium, which is always going to be, the alpha particle is always going to be helium-4, right? The remaining of what's being decayed is going to be based upon 2 less for the atomic number. And then the difference between that 4 minus the mass.
So pretty much what's left over after the release.
That is correct. Okay, so let's do something. So an example. So let's do PU. Okay, so, and it's going to go through alpha decay.
So are we always going to use helium?
Always, your alpha particle is always going to be helium.
Is
So
it,
alpha decay, it's always going to be helium.
and it's only one atom of helium.
Yes, it's usually only one atom of helium.
Okay.
So would it be niobium?
Okay. Are you?
Mm.
It would be 244 uranium.
Okay, so first off, it's that helium, right?
Mm-hmm.
Okay, so if we remove 2 protons from helium, then what do we end up? I mean, 2 protons from plutonium.
Oh, okay. Where's plutonium? Mm.
So you want to go 2 back.
Okay. Uranium?
That's right.
244.
Yeah. So you want to subtract,
2.
yeah, you subtract the mass number, right, from here. So that's going to give me 244. And then it's going to be 92, going 2 less than that. You see it? So these 2 add up to this. And then
Mhm.
these 2 add up to this.
Okay, got it.
Okay. Now, again, this is alpha
And
decay. What was
and
that?
the mass number is going to be different than the one in our periodic table.
Yes, because these are isotopes. It's a radioactive isotope. Yes. Okay.
And will this continue to decay
Yes,
till I don't know, like it reaches, let's see, it was like 90.
the stable, until it reaches its stable form, yes.
Oh, okay, so there's
Yeah, but
stable.
decay,
Got
yeah. So, but the thing is that the decay is gonna happen, you know, until it reaches a stable form. So this could actually even break down even more, right?
Mhm.
That potential, yes.
Okay.
So alpha decay is another word for alpha particle.
Yes, alpha particle. Alpha decay means that you're emitting an alpha particle. Okay. Okay, so we also have beta particles.
Mhm.
Okay, so beta particles are going to be high electron. High energy electron release. Okay, so in this case, we're going to be emitting an electron. So when we talk about beta particles, the way that they're written is they're going to be electrons. So it's going to be symbol E. You're going to have a negative value because electrons are negatively charged. And it's going to be 0 because it doesn't affect the mass. Okay. Okay, so let me give you an example.
So that's the equation for it.
I'm writing the equation now.
Oh,
That's the symbol for it.
go for it.
Symbol.
Is that a -1 on the bottom?
Yes. Let me fix that. So
And a 0 on the top?
a 0 on the top. Yes. So now, since this is a -1, in this case, we're going to end up with an extra proton to balance this out. So in this case, it's going to be 91. So if we look on our periodic table, see what is 91? I have an atomic number of 91.
Zirconium?
Atomic number of 91. Not atomic mass. Don't.
Oh. That's a long one.
What's the symbol?
PA.
PA.
Protactinium.
So PA
234.
234, because the mass is not going to be affected by that electron.
And can these various emissions occur at the same time?
Yes. So you could actually have a case where you end up with an alpha decay, which leads to a beta decay, and so you could have both of those occurring.
Okay.
Yes.
But it wouldn't be like thorium decays has like a beta emission as well as an alpha emission at the same time.
No, usually it's one or the other.
But then it goes into like a
It goes.
staircase of.
That's right. That's
Okay.
the sequence, yes. So it'll be sequences of reactions that are occurring until you get to a stable product.
Okay.
Okay. So, and then it could be, like I said, it'll be alpha maybe here, and then it'll be a beta. Then it could be an alpha, and then it'll be a beta, until it gets to something that's stable. Okay.
Okay.
So. Let's see. Okay, so let me give you an example. Say we have. Okay, write the nuclear equation for the emission of a beta particle from Bi 210. So bismuth 210.
Is it all right if we just put E negative, or should we always write the?
You should always write it the way it's written,
Okay.
because E negative, that means just an electron. Here, this is actually coming from the nucleus.
Oh, I see.
So it's from nuclear decay. It's not from
The cloud.
the cloud, yes.
Okay.
Okay,
So is it polonium?
that's right. So then if we wrote it, it would be Bi 83 210 yields E01 Z negative, sorry, -1. Excuse me.
Okay.
Polonium 84. Okay, not too bad, right?
Mhm.
Oh, what? So for the thorium example, would that be? Oh, okay. Sorry, I'm confused. Something. Never mind.
Okay. Okay. So our next example whiteboard. Okay. So this guy is called, it's basically, it's called a nuclear bombardment, or we can call it an induced radioactivity. So in other words, it's artificial, it's man-made, it's something that we do. It's not something that normally happens. So in this case, what we're doing is we're taking an alpha particle and we're colliding it with an atom or an isotope.
And what is this called again?
It's called nuclear bombardment or induced artificial radiation. Radioactivity. Okay, so in other words, we're causing it to happen. We're making it happen. It's fake, right?
Mhm.
So we're introducing that alpha particle and colliding it with the atom, that isotope that we're looking at. And then as a result of that, we're going to end up getting carbon-12 plus the release of a neutron. Okay, this here is basically called a radionuclide
So for this one,
yeah.
radionuclide is the neutron that was added, or the whole?
No, it was the neutron. So this here is called alpha particles. Remember the helium, if you have helium isotope, this is always your alpha particles. So we're heating it with alpha particles. We're adding alpha particles. And as a result of that, we're getting basically a fusion event, right? So we're kind of inducing something to happen. So we're getting the combination of Be
Mhm.
and helium coming together, right? So that's how we get its 4, its atomic number is 4, and then we're adding 2 more to it. So then that gives me an atomic number 6, which is carbon.
Mhm.
Okay, so this is an alpha particle right here.
Mhm.
This here is the radionuclide. Okay. So in other words, it's just a neutron that's being released. Okay. And so that has to happen for it to balance out, right? Because if we look at the mass, we have a mass of 9 plus a mass of 4. That adds up to 13.
Mhm.
So it has to, for it to be carbon-12, it has to release the
Okay.
neutron. That's right. Okay.
Mhm.
Okay, so fusion is going to be bringing things together, bringing stuff together to make something. So that was an example of fusion, right? Fission is splitting something. Okay, so if we go back to those first reactions, is this fission or is this fusion?
Can you go back to the other one,
Which one?
the fusion?
This one?
Yes.
Oh, okay.
So there's fusion and fission.
Mhm.
Okay.
So fusion is bringing stuff together to make an atom, and then fission is splitting something up, right? So usually fission is described as, because the other ones is like they have special names, but it's usually splitting stuff up to like two larger slices, taking a large nucleus and breaking it into two smaller nuclei. Okay, so this guy here, oops, sorry. This guy here, is this fission or fusion?
Which one? The one on the bottom?
Yes, the one on the bottom.
Oh, it would be fission.
Okay, the one on the side is also
Fission.
fission. Okay, so both are fission. What about this one? This one here.
Oh, fission.
Well, actually, this one wouldn't be fission because you're removing an electron. So that's kind of like a special case, right?
Oh, okay.
So you're not splitting up. Well, I guess you are in a sense, huh? Where actually it would be,
There's no other
yeah, there's no other element that's being
element.
added
Okay.
or being broken down. So, and what about this one?
Fusion.
Fusion. Okay. Because you're using the two of them to come together to make carbon. Okay. Okay, so fission. Here's another example. So let's have it. So here, we're adding a neutron to cause this reaction to occur. Okay, so here we're basically adding a neutron to cause the fission to occur. So we end up with strontium 94 and xenon 138, 139, and then we end up with 3 neutrons. Okay, so that would be an example of fission. Okay, and then one more. One of the most commonly used forms of fusion is the fusion of hydrogen. So we have 2 isotopes of hydrogen, hydrogen 2 and hydrogen 3, or tritium and deuterium. Iridium is being 2. Oops, I did 2 or 2. Sorry. We end up with helium. Okay, now this is a great fusion reaction. Because you're not left with any radioactive material. Right? And that's usually one of the benefits of doing fusion reactions, is because if it's done right, you produce a lot of energy, but I mean, if it's done right, you produce a lot of energy and you don't have any nuclear waste, something that's going to be decayed. Where fission, we typically get waste, and then that gives you more radioactive material that we're generating, causing more problems later on. So that's one of the advantages of using fusion versus fission. The disadvantages are it takes a lot of energy, a lot of heat to get it started. So you need put a lot of energy in just to get it kick started, but you get a lot of energy out of it. Okay. And currently, we don't have too many containers that could hold the amount of heat that's going to be required for it to be done consistently. Okay. Questions? Concerns? Cash?